Hello. So I wanted to take just a minute here and just briefly demo my project I worked on over the summer, just so that everybody kind of understands what it is that I'm trying to accomplish. So let's get into it. So my idea for a project was to write a backend in C, or C++, I should say, that transmits Morse code audio, series of dits and dashes. And as I work on this, I realize that there's an opportunity with another project that we're working on to control a robot with that code. So anyway, just kind of an overview of the code. Let's see, where's it at here? So for the front end, I'm using Python for now. Python has the ability to program in TK, which is the graphical front end with Python. So I wrote the graphical bit of that app in Python, and it ships with just standard input. It just calls to my compiled backend, which I've called AudioCW, and it sends just the text that you want to send and what tone, and then how quickly, the words per minute, so to speak, of your dits and dashes, how far spaced apart they are. And it sends it to the program, and your beeps are generated, and it plays the audio file. That's kind of how it works. So let's see the main implementation. And you've got a lot of really standard implementation, or a lot of standard imports, IOStream, some string manipulation dependencies, file system, the math dependencies, because we're actually doing the math, generating the sinusoids, and then doing digital signal processing inside the program to generate the tones and then ship them to a wave file, which is sort of like an MP3. And for that, for actually writing to the wave files, there's this soundfile.h, which is from this libsoundfile project, which I've had to look at the documentations on how to implement that here. And it's been kind of interesting seeing how that's done. I imagine that's kind of what VLC does in the background when you use VLC to play an audio file. I think it probably uses similar headers, but anyway, so my main program here, proceeds to take in arguments from the command line and then runs my different methods and whatnot to generate the audio file. And then the last thing that it does here, it prints audio out and then directs the front end to where that file is stored so that the front end can play it with, I chose to use MPV, which is sort of like VLC, but I think it's maybe a little more lightweight and easier for the program or easier for the computer to run. But anyway, so let me just show you now the installation of this thing. So I'm just going to download it, git pull, or no, I'm sorry, it's a git clone and the URL, which is available for anybody. Okay. So I made this pretty easy to compile. I used make, so all you have to do is do make, and it proceeds to compile the C++ program and set up the Python file for installation. It makes a build folder and puts all the stuff in there. So if we change directory to build, those are the files that it's going to install, these two here. There's only two files. Actually, there's a couple more than two files, I guess. I take that back. There's also a .desktop file so that it's indexable inside the start menu, I guess you'd say, and an image file that supports, so it gives it a nice icon. Anyway, now if we run make install, it needs password because we're using sudo, and it puts all the files where they belong. Now if we go down to start menu here, AudioCW. See, it's got a nice app. It's got a nice image and everything. It's a pretty nice app. I'm kind of excited for it so far. It's still got a couple issues I'm ironing out, but it does work. So here's the app. It's got a little window where you type in what you want to send. We'll just do hello world with an exclamation mark. And I think it also supports comma right now too. We'll try to make it exactly like traditional hello world. You can choose what tone it sends the audio at. By default, it's 710 words per minute, which is kind of your beginner speed, and 700 hertz is kind of the standard tone that I guess most of the CW is sent at. And I think you'll be able to hear it when I click play. Like so. And that's pretty much what the app does. And you know, you just change the text. I'd like it to eventually erase the text so that you can type new and maybe have enter instead of having to hit send, but it works. It works. So that's kind of what that looks like. Now we can actually test the back end too, and that's kind of cool to see what it generates. Let's see. AudioCW, yep, that's the back end. So the way the back end runs is like so. Hello world. And we'll just leave the rest at defaults. Why is that not working? Oh, I know, because exclamation mark is a special character in Bash. That's what it is. So we have to escape that. There we go. Audio out. Writes to, I just have it writing to temp right now. I think that's good practice. I don't know for sure, but that's the approach that I've taken so far, is that the temporary files it writes to temp, and then when the GUI portion is done, it just deletes it. But so if we analyze that sound file now with, I'm just using Audacity right now. It's not my favorite app, but it does work. When you open up that file, this is actually the audio and whatnot that the program generates with the methods that I've wrote. So you can actually see they're really perfect. No real world audio looks this perfect, but this is what the code is actually generating. And so when you zoom out, you can see the way that these tones are actually spaced is Morse code. So 4 small tones is an H, 1 is an E, L, L, O, W-O-R-L-D, you know, an exclamation mark at the end. So that's what it's doing, and it's really just playing that sound. So kind of the challenge from here is going to be, I'd like to have the other side, the receiving computer, be able to listen with its microphone and implement that all in C++ as well, to listen with the microphone on a specific frequency. So in this case it'd be 700 hertz, I guess, and to find that audio and decode it. And the idea is that it's using sound to replicate what an actual software-defined receiver does with real radio waves. So here's a SDR receiver that actually works with electromagnetic waves. So basically, for a student's project, this is doing pretty much the exact same thing, right? I mean, it's just using audible tones instead of radio waves, so it makes it more, you know, I don't know, academically friendly and whatnot. To, you know, you can hear it work, and it's to me it's interesting because I can hear the tones and I can see what it's doing, and it's easier to understand than trying to interpret what am I seeing, you know, coming in on one of these. And you know, I don't have to have nearly as much electronics equipment to do it. I think just a microphone and a speaker is going to be enough to be, you know, the microphone is quote unquote the transmitter and the speaker is the receiver. And what I've found out is that apparently in like submarine and underwater applications, they actually use ultra high frequency audible tones to transmit voice and whatnot between divers, you know, and submarines and stuff like that. They actually use sound. They transmit information as sound in a way that's somewhat similar to this. They're not actually using Morse code. They're using more efficient protocols. But again, I mean, this is an academic exercise. It's just something for a learning tool, and I think we can maybe combine it with the Bobot, wherever it is. There he is. So my thought has been to integrate it with another experiment that another student that I've been working with has been helping me with, and we've been working on together over the last, I don't know, a couple months or whatever, where we took this chassis and replaced the original hardware with a Raspberry Pi and a servo hat to make this an internet connected device, but also just more capable and more friendly to work and develop on. if we could mount some kind of a microphone to this, we could actually control this thing remotely. Like I've already got the driver inputted and everything to where all you have to do is supply it with a 3-line list of what you want to do, whether you want it to move forward, back, side to side, look left, look right. All that's already pretty well developed. We just need some kind of way to remotely control it. And we could do it over internet, but I think maybe doing it this way and writing basically our own audio driver controller, you know, whatever, control it with this Morse code thing that we were designing. I think that'd be really cool. So anyway, that's my idea right now. It might be it's a little bit crazy, but I think it could be kind of neat. So that's kind of where the project is at right now. And like I said, I'm kind of throwing around the idea, and I'm open to suggestions. We'll see what happens. So I wanted to look just a little more and explain just a little more in depth some of the electronics aspect of the project, and also some of the, at least what's in my mind right now, from what I understand, is kind of the algorithmic or the data structure side of things. So the Morse code alphabet itself is, I put this little infographic together here, is just a bunch of little dits and dashes. And the way it's set up is that each dit, which I've got represented with a star, is 1 time unit, and then a dash is 3 of those. So if you hear a dit, it just is like dit. And if you've got a dash, there's like, it's like 3 times the length in tone of this. So it'll be like da, you know, it's the length that differentiates one from the other. But really what it ends up being is binary, essentially. It's a binary that you can hear with your ear, right? And if you look at just the alphabet by itself, it doesn't look like there's any kind of structure or reason to it. Like why is A just a dit and a dash, whereas B is a dash and 3 dits, or vice versa? And there's kind of an interesting reason for it, but if it makes more sense if you look at it in a tree structure. So if you branch off based on which is a dit and which is a da, you start to see that, oh, this has to do with the frequency of how frequently the letter occurs in words commonly used in communication. And I guess it ends up being that E and T are the 2 most commonly used letters, followed by I and A. There's U. Basically, it seems like the pattern is that, and it's kind of cool that a lot of the vowels aren't very many levels deep on the decision tree, but it makes the Morse code alphabet look a lot more logical. At least there's a pattern to how it's laid out. And I think on the programming level, I could improve the data structure quite a bit by making it a tree like this, and when it receives the tones and whatnot, instead of having to look through a dictionary, it could look through a tree like this to figure out what the letter it ends up being resolved to. But the actual way the Morse code is physically transmitted, if you're really doing this over radio in the traditional sense, you've got this little key like this, and when you press down on the key, it completes a circuit, right? But I thought it was interesting studying this and trying to figure out how to make this into a project, that the actual connection of the key, so there's a little bitty tiny gap in between there, and when you push down on it, it just completes that circuit and completes that gap. And the signal goes over a little 3.5 millimeter audio cable like this, and literally just completes the circuit. This is a very, very simple little device. It's just like connecting 2 wires together, basically, and making it to where you can do that rapidly. But it's not actually the key itself that makes the signal, makes the tone. And I thought that was actually pretty interesting. And if I have time for all this, I'd like to explore that too, just for the sake of having an electronics portion of this to demonstrate that I did work in a project on. But so here's a diagram of an oscillator circuit, and you can see here's that same key, that little Morse key, in the diagram right here. So you've got your voltage source, your battery here, and some different components. But rather than going into how the circuit works or why it works, you know, just kind of understanding, like, okay, here's your circuit, here's your speaker that makes the beep or the tone, and in here somewhere in a fully put together circuit, this would eventually branch off, and you'd have your radio antenna and all of that as well. That would intermix the signal with your carrier wave and all of that. But it's neat that the way the tone is actually generated with a physical analog device is with this oscillation circuit. So the capacitor here charging and discharging at a known frequency, and then using this key alongside of it to turn the circuit on and off is actually what makes the buzz. The circuit makes the buzz, and the Morse code key is just what turns it on and off. And you basically just route that signal from all of that into the rest of your radio hardware, or in our case, it would be a speaker, which is kind of what's diagrammed here. And that's how the code is actually being generated. And so that's kind of what the C program is doing under the hood, is it's taking in those dits and dashes. Let me see, do I still have it pulled up? Where did my file go? Here it is. So the C program itself is converting text to dots and dashes based on I've currently got it set up like a dictionary or an array. I might change this later, but right now it just converts an A to a dot dash, or a B to a dot dash dash dash, etc. And then it routes through another function. It routes that information, a vector of all that. It routes that into another function that makes that into a tone. Where is that at? Right here. And it will, see here, it parses it out. If it's a dash, make this tone. If it's a dot or a space, make this tone. All the logic that is controlled here. And then my other function here does the quote-unquote digital signal processing right here, and converts it into a binary file, basically. And so you can actually see this if you go into your temporary directory. Let's see, where was it? Hex dump. Or maybe it's cat. Yeah, right there. Cat this. You see that it's a binary file. And it's not a binary file because it's the dits and dashes. It's a binary file because the wave file itself is represented in binary. So the way the digital signal processing works, and the values of the discrete values of the waveform at the sampling interval that you've selected are encoded in binary and sent directly to that file. And it ends up generating a tone, and I don't know, project's really cool. I'm super excited about it, and I want to see where it goes. But so I've got this idea for a project that's going to have, depending on how much time I have and how far we get in it, I've got ideas to try to control the Bobot with it, which would be kind of cool if I could attach a microphone to the Bobot and then issue commands through, a speaker like so to the Bobot and control it at a distance. That would be super cool. I've got ideas. I've ordered some circuitry components. I got that in today. They came from Europe over the weekend, to actually build a CW radio. Like I said, depending on how far I get, you could take the output from your sound card from this file and route it into that radio that I want to build, and transmit stuff that way. There's this project could go a lot of different ways, just depending on how much time there is and how much ambition I guess we end up having to do it. But that's kind of my idea right now. I'm excited about it, and I want to see where it goes. So it also turns out that this idea for a project that I've got is actually implemented in the real world in a more complicated manner, but the idea is essentially the same. So a lot of your emergency resources, fire department, police department, military, government, all of that, most of those people use digital radio when they communicate back and forth, and it allows them to talk over internet connected repeaters and do a whole bunch of cool things. But the way they do that is using these digital protocols. So here's one such digital protocol that's designed by a relatively big company, similar to cellular technology and whatnot, but instead of transmitting just FM signals like radio broadcast does, they use what they call a vocoder, which is essentially a more complicated version of kind of what I'm developing with the Morse code project, but it essentially sends these pulses, which are encoded and decoded with the CPU, probably using C or C++. And I've got just a really brief example of that, of what I recorded from one of the radios I have, done in FM and then in this digital mode using the same vocoder here. It's kind of interesting. Now, the vocoder and all the software and whatnot is actually proprietary. So, I mean, I couldn't work on that. I originally looked into doing this as a project, but I can't work on this because this is actually proprietary and is owned, it's intellectual property of this company. But, that's why I'm doing my own project, and I'm kind of going about it my own way. But this is actually where this is used, and they've pretty much just written a more polished version of the same thing, and just more complex. But the idea is essentially the same. So I just thought that'd be cool to show that as well. The practical application of this.
Kilo Juliet 5, Echo Quebec Romeo, test transmission.